All right, stats friends, we made it. This is the end. This is the final section, final chapter, final everything. So we're going to be revisiting ideas about linear regression lines and then trying to figure out how that plays into our inference. So we're going to be looking at inference for slope today. Now, this lesson's a little tricky because there's a lot in it, but as far as what you're going to be required to do on the AP exam, it's a little less involved than the lesson indicates. So there's a few learning targets here. Checking the conditions for inference for slopes is probably one of the hardest things to do in this lesson. The conditions are a little tricky, but we're going to kind of zone in on what that would look like. And then we're going to interpret the values for A and B and S, and then the standard error for our sampling distribution for slope. And then, of course, in context, and determine how we can find all those values from computer output. And that's kind of the big thing today, is it's not so much the calculation of everything, but it's the interpretation and also being able to create something from a computer output. That's the big focus. So we're going to do confidence intervals and also significance testing to figure out the parameter values for the beta slope, which would be the true population regression line slope, which of course we rarely know. So there's an example, and this is actually the same example that Mr. Starnes goes through on AP Classroom, and he takes this same example and kind of builds the whole lesson this way on AP Classroom. So if you're not liking what I'm throwing down, go ahead and watch those AP Classroom videos from Mr. Starnes. But this is the duration of time in between the next eruption for Old Faithful. So this scatter plot would be 263 eruptions within a single month. And this is the population least squares regression line for that particular time. So it's all of the eruptions given, or recorded, I should say. The regression line calculated for the population is called a population regression line or a true regression line. And the formula that we're going to be seeing, resembles what we already know about regression line, but it says mu sub y, meaning it's the mean y value for like the whole population, right? And then that A is an alpha. It's a little curlier than an A, right? So it's alpha. And then that capital B looking thing, that's a capital beta. And that's going to represent the the population slope for the true regression line. And then alpha is the population y-intercept. So everything we know about regression is still the same. We just have to kind of differentiate between a population regression line and then underneath there, the sample regression line. The sample regression line is exactly how we saw it back in chapter 3. So y hat meaning the predicted or the estimated mean y value for a given value of x. A is still the sample y-intercept. We're going to use the sample word this time, and then B is the sample slope. Back in chapter 3, we didn't indicate like, oh, sample population, what are we looking at? Because we weren't that far into our curriculum. So let's talk about scatter plots and then least squares regression lines versus the population lines. So what they have this time is 3 different simple random samples of 15 eruptions plotted against the population. So the population is the blue line, that's the true regression line, and then the sample is given there in the green line, and that's based off of those 15 samples that they took. So obviously not like a dead ringer fit, but we know it's an approximation. So the sample line has been calculated for you with a y-intercept of 44 and a slope of 10. And then here's a totally different one with 15 different simple random samples taken. And then again, you see a different y hat, right? So a y hat equation. So you have 39 plus 12.5, so different y-intercept and slope. And then here's a third example where again, different from the population, different from each other. But we know this is due to sampling variability, so this is not a big shock. So the slopes are kind of not the same, and they're definitely not the same as the population, the overall population's regression slope, which was about 13. But we know that's due to variability. So what they're going to do here is they're going to show you a whole bunch of simulations that obviously they're not going to like literally do these samples. They're going to simulate them. Otherwise we'd be there forever. And they're going to notice some things about this sampling distribution. So, I should say the simulated sample distribution. Uh, It centers around the true population slope, which is 13.29. And this is exactly what happens in sampling distributions that, you take enough of them or you simulate enough of them, you're going to see it kind of centering on the true mean, or in this case, the true slope. So the shape is approximately normal and the center is where it's supposed to be, meaning that B, the sample slope, is an unbiased estimator of beta, the population slope. Now, variability gets a little kooky. That formula is on your formula sheet. There's a whole section for this, inference for slopes business. So if you ever do have to hand calculate it, this is how you could do it. But a little foreshadowing, we're going to pretty much be given this information on computer outputs, and that's what we're going to have to worry about. Now, sigma sub x, remember that's the standard deviation for all the durations, the 263 eruptions. Sigma sub b here is us calculating a variability for our sampling distribution, or in this case, our simulated sampling distribution. So there's the formulas again, all in one spot. And this is something, again, you can find these on your formula sheet. The only exception is like it's not going to differentiate like sample versus population. So we got to be careful in our notation. And then this is the part that I think is the most challenging part of the lesson for kids to understand. It's the conditions checking to make sure inference is met. Now, I have it on good authority from people who've been doing this much longer than I have, and they have said typically when this sort of question would show up on an FRQ, the question says, please assume that all conditions have been met. So that makes me feel a little better because the conditions checking on this one is kind of laborious. But what I would expect to see is maybe a multiple choice question that directly talks about one of the conditions and how we can check for that, like individually. So I think it's worth a look. And obviously, you guys are smart, so it's always worth a look because you guys like to connect your ideas. So the line is the true regression line. Okay, that red line there is the true population regression line. And you're going to notice that for each particular value of x, they've created this like extra like distribution along that point. So like for whatever this, oh, where's my cursor? So whatever this x sub 1 is, you'll notice if I follow it up to the line, it's going to be centered at like the center of that distribution, which we know is supposed to be beta. So it's going to follow a certain predictable pattern, thus the prediction line. For any fixed value of x, the observed response variable y is going to be varying according to a normal distribution. Okay, cool. Let's see what this looks like. So this is why the conditions check is a little laborious. There's more conditions and they're kind of weird. They're not in any particular order, but they make a cute little acronym or mnemonic device, I should say. It says LINER, so liner. We're supposed to remember liner. So linear just means that there is an actual relationship that is linear. So if you're looking at the plots, the scatter plot, and you're like, you know what, that doesn't look linear, then you shouldn't be doing this type of inference. Independent, just meaning that the individual observations are independent from one another, and then also remembering that if you're sampling without replacement, you have to check the 10% condition there. And then normal, meaning that for any particular value of x, the response variable, which is y, is going to vary according to a normal distribution. And we'll check that on a residual plot. A lot of these get checked on the residual plot. So that's an old idea coming back. Equal standard deviations, calling it sigma here, they're going to be the same for all values of x. So again, we're going to be checking that on a residual plot. And then the random condition is just that the data was coming from a random sample, or if it's an experiment, they're randomly assigned. So that's an easy one to check. The rest of them, like linear is not hard, right? You just look at a scatter plot. Independent should be kind of obvious from the context of the problem. And then normal and equal standard deviation, that's going to come from us looking at the residual plot. So which brings us to another idea. Do you remember how to get a residual plot? And we'll talk about that more in class. But typically on these questions, they're going to give you the residual plot. So here's two examples of two different problems. And if our first question was like, hey, do you feel like this data is linearly associated? So this particular problem about miles driven versus price, I don't know what the context was in this question, but ignoring the blue line, the data itself, if you squint, it does look like it has a negative linear association. But this one, and this careful, this is a residual plot. There's a leftover curvature, so that tells you that this data is not linear, so we wouldn't be able to continue with this type of inference in that case. Independent, They're just going to kind of mention things that we kind of already know about. This is what's nice about this chapter, or these past few chapters. Knowing the value of knowing the value of the response variable for one individual shouldn't predict the value of the response variable for the other individuals. So they have nothing to do with each other, basically. Yes, they are related to the line that we're creating, but they are not related to each other necessarily as far as prediction goes. And then also the sampling is done without, if it's done without replacement, you have to check the 10% condition. If you're sampling, right? That only works for samples. So for normal, they want you to make a histogram, dot plot something of the residuals. So that's a little tricky because if you're doing this on your own, you have to first find the residuals and then actually plot them. Now, usually that happens on technology, but like I said, usually these questions are given in a way where they give you the plot and you don't really have to do much work. So that's pretty nice. So here's how we're going to check for equal standard deviation. So we're looking at residual plots. And then remember, zero is meaning like there's no variability in the data. And you're going to see your scatter plots kind of have a nonsense hot mess pattern, and that's when you know you have a good residual plot. The other thing to look for is the variabilities in the vertical direction is about the same at that particular x value. So like um, this is they're saying a good example. The residuals have roughly equal variability at all values of x. I know there's some weird random ones that you're like, oh, that doesn't really fit, but it's okay. Now this is a bad example because as you move out in the x direction, you see the residuals are getting bigger and bigger and bigger. So that's not going to work for this equal standard deviation conditions check. That would be an example of a failed condition, and we wouldn't be able to move on. But remember, the point of this is you want to be able to move on. So keep that in mind. Random, the data has to be a random sample from the population of interest, or if it's an experiment, it's randomized with the assignment. And again, if you don't randomize it or you don't select randomly, you wouldn't be able to take your inferences and apply them to a larger population. And as always, we got to worry about association versus causation. Whenever the word cause, like causes, does this cause a change? We have to be careful about how we set this up. Remember, you can only infer causation if it's a randomized experiment, a comparative experiment. So here we have a class about Ms. Barrett's class, and they're using paper helicopters. That sounds fun. We should do that. All right. After making 70 helicopters using the same template, students randomly assigned 14 helicopters to each of the 5 drop heights. And then there's various drop heights. Teams of students released 70 helicopters in random order and measured out their flight times. So you'll notice at each of the drop heights, there's like a bunch of dots, bunch of dots, bunch of dots. And then here's the residual plot for that same data. And then this is them. This is what I mean. They're just going to give you this. So this is the histogram of all the residuals. So you physically didn't have to make that. They're kind of providing this to you. So we're going to check the conditions. So first condition in any order, technically. Linear is a good one. I just go in the order of the acronym, LINER. So linear, yeah, this and again, remember these are a bunch of data points from the same drop height. That's why you're seeing it. But if you kind of squint, yeah, it's definitely a linear pattern. So the scatter plot shows a clear linear form, and there's no leftover curvature when you look at the residual plot. So linear is looking good. They are independent because the helicopters were released in this random order and no helicopter was used twice. I think we've all done that where like you've had a cheapy toy or something and like you flew it one time and then you flew it a second time and it like crashed and burned. Um, so we're not going to have that issue because they're only going to fly each helicopter once. And then knowing the result of one observation shouldn't help you predict a different observation. Um, no predictions yet. All right, normal. If you look at the residual plot histogram, you'll notice that there's no skewness, no strong outliers, so that's a check on the normal. And then for equal standard deviations, I know something kind of weird happened here at the 300 drop height, but if you kind of look amongst them, it looks pretty good. There is something weird happening with the residual variability here at 300, but we can investigate that with a different sort of experiment or study. But for now, we're going to say, sure, good enough for the equal standard deviations check. And then random. Remember, the helicopters were randomly assigned to the different drop heights. So they didn't pick their finest and best and purposely put them anywhere. So we checked LINER, check, 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 check. Moving on. And then warning, don't overreact to minor issues. So like that drop height of 300, like some kids are going to say, oh, I can't move on. That's not the point of these questions. So you want to be able to move on. So even if it's like slightly weird, just be like, you can mention it, but just say, let's move on. When the conditions are met, then you can go ahead and do inference. So the two types of inference we're going to look at as always, are hypothesis testing, but first we're going to look at confidence intervals. So the first step is to estimate the unknown parameters. So like we don't know alpha and we don't know beta, but we do know um, some sample data, right? We know the sample y-intercept and we know the sample slope, and we can figure out residuals to figure how much is varying from the population. So we're going to use, and this looks confusing because they look the same, but that is A estimates alpha, and B estimates beta, and S, standard deviation of the sample, will estimate sigma, the standard deviation of the population. So we threw this formula at you earlier in the lesson, and again, it is on your formula sheet, but remember, that's assuming we know sigma, right? And as we do inference, we realize, oh, snap, we don't know sigma. So also on your formula sheet, you're going to see right next to it the standard error of the slope, which is what we have to use when we're using sampling distributions because we don't ever know sigma. So instead, we use S. Um, and then this gets a little confusing because you're like, there's an S and there's an S sub X. These are going to be two different things. We'll talk about that in a minute. The standard error is interrupted as how far the sample slope typically varies from the population slope if we repeat the data production process many times. Or sorry, not interrupted. Oh my gosh, interpreted. Hello, I need help interpreting. So the standard error, this is what I think is one of the hardest things for kids to interpret properly because we often forget that little thing at the beginning. Anytime you're talking about a sampling distribution, the idea is that you're taking many, many, many samples of the same size. So if all your samples were 15, after repeatedly doing this many times, taking samples of 15 every single time is kind of the first way we start that interpretation. And that's something I tend to forget, which is a really big deal because they're going to get marked wrong. Also, if this was a multiple choice question, they would probably try to distract me by giving me an answer that looked good, but it didn't have that, for many samples of size 15 at the beginning. Okay, this is a great example of what a question might look like. So they have a computer, a Minitab output here, and we're back to that paper airplane or helicopter question. So recall this data came from dropping 70 paper helicopters from various heights, and they were measuring flight times. So if you think about your variables here, you'll see flight time versus drop height. So flight time is your if you want to think of it as your y value variable, your response variable. Drop height would be like your x, and the other way to remember that is, they're going to give you a variable written out here in Minitab, and that's always going to be your independent variable, if you want to think of it that way. Your x, which means that we're staring at, just spoiler alert, we're staring at slope right there. There we go. All right, so it's been a minute since we looked at these Minitab outputs, and that's how these problems are probably going to look for us. We got to get used to this. So first, what is the estimate for alpha? Remember, we don't know alpha. So we're going to use A to estimate alpha, and remember A is the y-intercept. So the constant coefficient, um, where are you at, buddy? I feel like something weird happened here. This is a typo. Oh, guys, I don't know what's going on here. Don't make me review this. Oh, it's in centimeters, seconds, seconds. Something's weird here. I don't want to have to redo this. All right, this says A equals 20.03. I don't even know where that's coming from, other than that's a big old typo. Okay, we'll come back to that. um, so what they should have done here is A, remember the way our formula is set up, A is our y-intercept, and it's about when your helicopter is dropped from a height of 0, how long will it take for it to land on average? So this, something's not matching here. I'm trying to figure out where the mistake's happening. I don't know if this is the wrong mini tab or if this is just wrong. Guys, I don't know what happened. Oh, this is embarrassing. Preview your slides, girl. Come on. All right. Anyways, let's look at the format for how they interpreted it because the format's right. So if a helicopter is dropped from 0 centimeters, it would take, now this doesn't even make sense, 20 seconds to land on average. Like, no, that makes zero sense. What at all? Oh my gosh, how embarrassing. All right, we'll come back and fix that. All right, now this one, let's see. Okay, this one actually is right. So we talked earlier about how the coefficient for the drop height, this is fancy talk for slope, because I think of, okay, this is the x variable and the coefficient in front of x is known as slope for us, right, in math? So this is correct. And it's a little difficult because kids are trying to figure out how this relates to what we did in chapter 3, where we had to talk about like predicted and whatnot. Now, remember, this is a sampling distribution, not like a prediction. So we're going to use the word average. That's the thing we have to sneak in, right? So for each increase of 1 centimeter in drop height, right? So slope is y over x. So we always assume the x is a 1. The average flight time increased because it's positive by 0.0057-ish seconds. So not very much, but obviously it does have a positive linear relationship that we were looking for when we saw that scatter plot. All right, I'm still wondering where that 20 came from. What a mystery. All right, so that burns me. All right, let's talk about S. So S is what we're going to use to estimate sigma, because remember, we don't know sigma. Now, S is given to you on the Minitab output right here, and that is going to be the measure of variability. And you got to stop and think about what we're measuring here. So here's the template we're going to use for interpreting S. So the actual flight time typically varies, that's a standard deviation thing, right, by about 0.17-ish seconds from the times predicted with the least squares regression line using x equals the drop height. And that is very much in line with what we did back in chapter 3. So when we interpret a standard deviation or some sort of variability, we talk about, okay, what are we measuring here? So the actual flight times typically varied by this amount from the predicted when we use the least squares regression line, and then they like you to determine who your independent variable is, who your x is. I feel like that's a topic we need to revisit. It's been a while since we did that. Now they want us to talk about the standard error of your slope, which again, you're like, oh man, how do I get that? Well, you could use that calculation we showed you, but actually it's right here on your mini tab. So see where it says SE coefficient? Boom, there he is right there. So there's your standard error for your distribution, standard error of your slopes. So if we, and here's the part that I always forget, so we got to be careful. If we repeat this, and it was random assignment, if we repeat this random assignment many times, the slope of the sample regression line would typically vary by this much from the true slope of the regression line for predicting flight time. So again, that interpretation of variation hasn't changed. The only thing we had to sneak in here is that we repeated this process many times, because anytime you work with standard error, that's because you're looking at a sampling distribution. So you have to make sure you indicate you're doing this not once, not twice, like 500 times, right? Many, many, many times. Sorry for the typo and my blunder. That was my bad. Hey, there's an old friend. Now I'm building back my confidence, no pun intended. That's our formula for finding confidence interval. So it's going to be found the same way for slope. The only thing you have to think about is like, what's my statistic, and then what's my standard deviation of the statistic. So B, the sample line, sorry, the slope from the sample line, there we go. B is what we're going to use as a statistic. Hello, plus and minus T star, because we are using a T interval. And then that standard error that we were just talking about. Now, a little special today, the degrees of freedom, if you're doing this using table B, you're going to have to use n minus 2 degrees of freedom. Okay, so whatever the number is, but take 2 off of it because we got to be a little more conservative than normal. And then that's going to help us by hand find the T interval. However, the values for the T interval are actually on the computer output typically, but they're warning us here. What does it say? The computer regression output are not the critical values for the confidence interval. Yes, that is a good point. So we have to be careful, because sometimes like the letter T shows up a lot in our stats book and we're like, wait, which T is this? Is this T star? Is this a T score? Like, what am I looking at? We'll talk about that. All right, so here I think they're going to have us do a little bit by hand. Again, please rest easy. You're not going to do much of this by hand. So I think we had this problem back in chapter 3. We're looking at those Ford F-150 Super Cruise, and we know how many miles on the odometer would we be able to predict the price. We totally did this problem before, I remember. So we have a random sample of 16 used Ford F-150s, and then here's their information. And the number of miles driven and the price in dollars is recorded. So we're going to be talking about a prediction line. And what they have here is a computer output, so that's helpful. They also gave us the scatter plot, which does show a negative linear relationship. They showed us a plot of the residuals, which is a hot mess, so that's good. And then here's a distribution of the residuals, which I don't see any crazy skewness or crazy outliers, so that's probably going to be a conditions check in a minute. All right, so they're going to go through the four-step process for finding a confidence interval. So this is what it would look like. So we are finding a 90% confidence interval for beta, which is the true slope, right? The slope of the population regression line that relates the price to the miles driven for used Ford F-150 Super Cruise. Cool. So basically, we just restated the question. We did have to indicate like what our line was set up as though, because we know from our work with linear relationships that you have to indicate who's X and who's Y. Now, here's the conditions check, and this is, again, a little laborious, but they shouldn't have you do this on an inference question for these, so that's the good news. So linear, the scatter plot was definitely linear, and the residual plot showed no leftover curvature, so check. Independent, 16, I'm sure, is less than 10% of all used Ford F-150s, so that's feeling good. There was no strong skewness in the histogram of those residuals and no outliers either. And then if you think back to the residual plot, um, they were really scattered. You didn't see any like increase in residuals as you went down the lines for miles driven. It's not like it got small or big in either direction. So that's feeling good for the equal standard deviation. And then random, we did randomly sample the 16. So check, 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 check. This is them doing the confidence interval by hand. So degrees of freedom would be 14 because sample size minus 2. T star came off of table B, so 90%, T star for the 14 row is 1.761. This number right here, this negative 0.16292, that came off the computer output. So that came off of, remember, B is slope. So miles driven coefficient, boom, there's your slope right there. So that's B. It would just be too beautiful if they called it B, but they didn't. So that's what goes in our statistic part. And then follow the formula. So here is our T star. And then this number right here, this is our standard error of the sampling distribution for slope, which is right here. So standard error coefficient, boom. So it's right next to slope, which is handy. And notice like there's some T's on this, but it's a capital T and not T star. So this is not the T that we're looking for. This is not the droid you're looking for. Haha, that's a Star Wars joke. All right, so then we can continue on with our confidence interval calculation. We found the margin of error, and then we start by subtracting it off first, and then we add it, and then we get our confidence interval. So of course now we're going to conclude. We are 90% confident that this interval captures the slope of the population regression line that relates the price to the miles driven for used Ford F-150. So again, from that point on, you're just kind of restating what you already stated earlier in the problem, and everything else follows what we know about confidence interval conclusions. Something to point out, and I think Mr. Starnes does a really good job of this in his videos in AP Classroom. If I look at the slope, we're going to talk about hypothesis testing soon. The confidence interval there contains only negative values. So it doesn't go through zero. It doesn't all of a sudden change to positive anywhere in the confidence interval. So that's telling me that we have some good evidence towards the fact that there is a negative linear association there, which we already knew, but now we're actually proving it with statistical evidence. So of course, there are some calculation options on your calculator. So linear regression T interval is found in the, I'm guessing the test menu, so stat test. And you would have to have your data into list one, list two, and then enter in all the information. Like I said, this question typically is not, do everything from beginning to ending. It's going to say like your conditions are met, or so entering the data might not be a good idea because if you look ahead in the question, you might be doing extra work that you don't need to do. If they already gave you the computer output, you should be able to calculate everything really quickly. And that's their warning here. Often the information is already given to you. So you shouldn't be entering all that data. It's going to take a lot of time that you just frankly can't afford on the AP exam. So here's a check your understanding question. And there's a regression analysis. Ooh, it's blurry, sorry, coming up. So noting their note from earlier, do not enter all this data in your calculator. That would be a waste of your time. So does sitting closer cause higher achievement? So they want to study this. To investigate, a stats teacher randomly assigned students to seat locations in the classroom for a particular chapter and recorded the test scores for each student at the end of the chapter. Here's the data. Along with output from a regression analysis, construct and interpret a 95% confidence interval for the slope of the true regression line. So what we have here is a scatter plot of the data. We're going to say it's linear. It doesn't look super linear, does it? However, the residual plot looks pretty messy, so that's good. And then they also took the time to graph the residuals on a dot plot distribution, and they gave us a sort of a mini tab output. So that's all going to be helpful. Something to kind of point out is, row number is our x and test score is our y. So as far as which variable's which, the row coefficient, this is slope. This is the standard error for your slope. This is S if you need it. And this constant coefficient, that's your y-intercept. If you're looking for values, that's probably the only ones we're going to use. Oh, those friends are coming back soon. And these are not the t's we're going to use for confidence intervals, so don't look at those. All right, so here's all the answers. 95% confidence interval for beta, which is the slope of the true regression line relating score to the row that they sat in. So we are finding what's called a t-interval for slope. If you wrote it in other words, it's fine, but t-interval for slope works. So they checked all the conditions and they all look good. You can pause the video now and kind of look at them more closely. It does say that the amount uh, of scatter points around the residual varies somewhat, but it's still plausible that, you know, there it's a decent enough variability that we can continue on with the, the T procedures. Because remember, if we can't, then we'd stuck. So all those conditions were checked. The degrees of freedom is 28. So they found a T star value of 2.048 from table B. They used, let's see right here, this is the slope from our computer output. Oops, back up. See this guy right here, row coefficient. And then the T star they just found. And then this 0.947 is the standard error, which is found right here, the row standard error. So the slope standard error coefficient. Ugh, it's confusing, I know. And then they calculated the confidence interval. Here he is. Now you could have done the calculator and found the confidence interval. They use the same degrees of freedom, of course. And then we're 95% confident that this interval captures the slope of the true regression line relating these two variables. And then it does say for students like these because, the scope of inference was limited to these particular students. I'm going to be honest, that was kind of a silly study. I don't know if that information is that exciting. All right, so now we did talk about confidence intervals. So of course now we got to talk about hypothesis testing. So that's an old friend, standardized test statistic minus parameter divided by standard deviation of the statistic. So for the null hypothesis, it's that your slope is equal to the hypothesized slope, which we'll talk about in a moment. And then the alternative we'll talk about in a second. But for now, just know that your t-score is found just like how you thought it would be found. So you take your sample slope minus the hypothesized slope, and you divide it by the standard error for slope. Again, we're going to rely heavily on computer output for these. And actually, I think you'll be even more excited about the computer output here. So oh, that poor baby. All right, infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. Oh, all right. Child development researchers explored the relationship between the crying of infants 4 to 10 days old and their later IQ scores. A snap of the rubber band on the sole. Oh my God. Why? They snapped the baby's foot with a rubber band, caused the infants to cry. The researcher recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. What? Oh my gosh. Okay. They later measured the children's IQ at age 3 using the Stanford Binet IQ test. Awesome. The table contains data from the random sample of 38 infants. Oh, this sounds great. All right, here is the computer analysis, followed by some scatter plots, the scatter plot of the residuals, and also a distribution of the residuals. So, do these data provide convincing evidence at the 5% level of a positive linear relationship between crying peaks? So, this is a clear indication that we need to perform a hypothesis test, regardless of how sketchy this study sounds. So we're going to begin with the state step. And this is what I think might be new for your brain. So the null hypothesis is that your beta is 0. Now think about what that would mean from algebra. If your slope of your true regression line is 0, that is not a linear relationship, right? Like it's a line, but it's a horizontal line. It's not like a diagonal line, if you want to think of it that, meaning that there's going to be a consistent non-change as you move from, you know, variable to variable. However, their test was, did we see a positive linear relationship? So the alternative hypothesis is that your slope is greater than 0 because we know a positive slope would indicate a positive linear relationship. Oh my goodness. I'm still kind of scarred that they're snapping the baby's feet with rubber bands. Okay, so beta is the slope of the regression, the true slope for the regression line, where it relating, excuse me, the IQ score to the count of crying peaks in the population of the infants at the 5% level. Oh God! All right, checking the conditions. We are going to perform a t-test for slope. And the data is pretty linear. If you look at the residual plot, there's kind of a hot mess going on. So at least we don't see that leftover curved pattern. So check on that one. 38 is less than 10% of all infants, I'm sure. And the residuals were plotted, and there's no strong skewness, and there does seem to be like a bar off to the side, but we're not going to consider that an outlier, simply because we need to move on. So just say there's no clear outliers there. All right, equal standard deviation, you'll notice in the residual plots, they're kind of, it seems to get kind of bigger here, but we are just going to continue on and say it's fairly equal. Otherwise, we wouldn't be able to continue. And it was a random sample of 38 infants. I know this felt like an experiment because they were snapping their heels, but they weren't doing anything as far as comparative. So they were just snapping their heels with a rubber band to get them to cry. Yikes. All right. Anyways, t equals 3.07. Boom. Look at that. I love hypothesis tests for slope because it's right there. You don't even have to calculate it. The p-value, now this is where it gets a little tricky. This p-value that's on your computer output always assumes you have a two-tailed significance test. So if you only have a one-sided significance test, you have to cut it in half. So the p-value is not 0.004 for this particular one, because remember it was a greater than 0 alternative hypothesis. So you need to divide it by 2. So the real p-value is 0.002. So here's our conclusion. 0.002, our p-value, is less than alpha of 0.05, so we reject the null hypothesis. There is convincing evidence of a positive linear relationship between the count of crying peaks and IQ score in the population of infants. I'm so glad you tortured these babies so we could find that out. Oh my gosh. Ugh. All right, so linear regression t-test is something you could do if you're forced to do. You'd have to enter the data into your X and Y for list 1, list 2. And then you'd have to set up everything, and it's pretty obvious what they're looking for. Now, you can store your regression equation into Y1 if you wanted to, but typically we're not even going to have to do these steps, so I'm not going to talk much about that. But it does give you all that information, the t-score, the p-value, degrees of freedom, and A and B and S. But, if they're going to have the computer output for you, then I say we just go with it. Like here's another example. We have the computer output. So if I'm kind of differentiating between what we have here, what do we have here? Oh, it's that seat experiment again. All right, so we know that we're going to perform a hypothesis test. So the important things to me are going to be p-value and t-value. So this here is your t-score that we would have calculated. And then over here is a two-sided p-value. But we're going to have to figure out what kind of hypothesis test we have. So do the data provide convincing evidence at the 5% level of a negative linear relationship? So this is going to be a one-sided hypothesis test. So the null hypothesis is that there's no linear relationship, and the alternative is that your slope is less than 0, meaning a negative linear relationship, where beta is the slope of the true regression line that relates the score versus the row that the student is in. And then 5% significance level. I always forget that. All right, t-test for slope. And then, oh, it stated that the conditions were already met because remember we checked those. So check. So we are just going to look at the output and say, according to the output, the standardized test statistic is t equals negative 1.18. And because that output gives you a two-sided p-value, we just have to cut it in half because ours is going to be a one-sided. So 0.248 cut in half. And remember, those numbers came from right here. So here's your t-score, and here's the p-value for a two-sided hypothesis test, which we only wanted one side of it. Now, our p-value is greater than alpha, so we fail to reject the null hypothesis. There is not convincing evidence of a negative linear relationship between row and score for students like these. So this is giving us evidence that for these kids, it didn't matter where they sat, their test scores were not affected in that direction. All right, so it did ask some other questions about errors. A type One error is where the teacher finds convincing evidence for a negative linear relationship between row and score when the true slope really is 0. And a type 2 error, remember, would be that a teacher does not find convincing evidence for a negative linear relationship, but actually it is the truth. So, because we failed to reject the null hypothesis, it's possible we made a type 2 error. That means we didn't have convincing evidence of that negative linear relationship, but in actuality, it's true. And if you think of it in context of this problem, the teacher might be living her merry life thinking, oh, it doesn't matter where kids sit, when in actuality, sitting in a certain spot in the classroom made a difference on test scores for some of these kids. Oh my gosh. I feel like celebrating, guys. That's it. All right, so just kind of summarizing this particular section of this chapter, it's very heavily influenced by computer output. It's not a lot of calculation. I mean, I love that you guys could calculate it if forced to, but the conditions, the residual interpretation, and then all the interpretations of the variables, can you interpret A and B and S and then the standard error for slope? Those I think are some of the trickier parts of this lesson. Computing is not important, I guess, for us as far as the AP exam goes. It's the interpretation of what's already been computed. That's the kicker, right? Guys, it's been a time. I've enjoyed it. Thank you so much.